Hi everyone, thank you for coming for the 10th lecture in network security. So we started nicely, we spoke about symmetric, right? We spoke about asymmetric cryptography where we have one key, secret key. Now we're going to talk about asymmetric where you can have two keys, one called public and one called private, right? In the asymmetric encryption, we don't call it public and private, we call it secret key. Secret key, because it's secret key. And here we call it public because one of them is public, everybody knows, and one is private for you, nobody else to know. So we'll see, we'll give you a comparison and how it works and all of that, okay? So symmetric and asymmetric key cryptography will exist in parallel. So there is nothing called old technology and new technology. They are exist in parallel. They have different applications. So we use them all together all the time and continue to serve the community. We actually believe that they are complements each other. Okay? The advantage of one can compensate it for the disadvantage of the other one. We'll see that. Okay? All right. So basically, in the symmetric and asymmetric key, the symmetric key cryptography is based on a sharing secrecy. Sharing secrecy. All right? Asymmetric key cryptography is based on personal secrecy, one secret key. And here we're going to share a secret, which is a public key, as we will say. So asymmetric key cryptography uses two separate keys. The first one we call it private, which is private. And the second one is public, which is public. Everybody knows about it. All right? So look in here what will happen. So Bob would like, okay, where is Bob? This is Bob, right? And this is Alice. So Alice wants to send a message to Bob. And the only person needs to read it is Bob. So Bob has a public key somewhere, everywhere, in his web page. So Alice takes Bob's public key and encrypt the data. So Alice encrypted the data with Bob's public key. Once you encrypted with Bob's public key, the only way to read it back using what? Bob's private key. All right? So it will be sent in the communication channel. Okay, all right, it's gonna come in here. So Bob will use his own private key to read the message. All right, so now when I encrypt with the other person public key, with the other person's public key. As simple as this. Done, we finished. Public key, private key, and they have to work together. So if you lock with the first one, you can't unlock with the other one. Where is the problem? Is there a problem? How we can choose the keys? How we can choose two keys that one work with the other one? Right? That's where the algorithms come, right? All right. Let's continue. So what will happen in here? We're going to have something called key generation procedure. So in the key generation procedure, we'll issue two pairs. One is public and one private. So the private will remain for that person, and the public will be shared to everybody. So the public key distribution channel. All right? And so again, in here, if Alice would like to send a message to Bob, she has to get the Bob's public key and use it to encrypt the data, send it in secure channel. It will be received, and Bob will be able to read it through private key. All right? So before encryption and decryption, we have something else, which is key generation. Key generation. And we have to share it in the public.
I didn't get that.
Okay. So Bob has to generate two pair of keys, public and private. The public will share it to everybody. So Alice can know it, John can know it, Noah can know it, Susan can know it. Everybody can know the public key. The private will remain with Bob. So Alice would like to send a message to who? To Bob. So it has to go to get the public key, which is posted somewhere. Use it and send the data. Bob will use a private key to, okay? All right? So we have to generate, Bob has to generate 2 keys. All right? So there is an algorithm for key generation. And there is algorithm for encryption. And there is algorithm for decryption. Before, we had algorithm for encryption and decryption only. Now we have to have algorithm for key generation. All right. So, as you know, there is a plain text and cipher. So, unlike in symmetric key cryptography, plain text and ciphertext are treated as integers in asymmetric key cryptography. Before, it was a string of digits. In here, it's integers. It's integers. So we have to convert our data into integers. Why? Before, what we used to do, permutations, right? Substitution and permutations, right? In here, we do mathematical operation. So mathematical operations, you do it in what? In alphabets or in digits? In digits. So the data has to be digits. So exactly what you're going to do. So to generate the ciphertext, you're going to have a function. The input to the function is the plain text and the public key. Using the public key, you could create the ciphertext. To get the plain text, you're going to have another function called G, using the private key and the cipherlink. All right. So there is a very important fact that is sometimes misunderstood, which is the advent of asymmetric key cryptography does not eliminate the need for symmetric key cryptography. All right. Symmetric key cryptography is used for what? For hard disk encryption, for message encryption. Okay. The asymmetric key used for digital signatures, for different purposes, as we'll see in a second. Right? Okay. So the main idea behind asymmetric key cryptography is the concept of the trapdoor one-way function. We are using function. Function is a math function, which deals with digit. So what kind of function we're going to use? Called one-way function. Okay. What does mean one function? You could go from x to y, but you cannot go from y to x. So for example, in here, a function as a rule mapping a domain to a range. So we have a domain and elements, and we have a range and elements. So we could go x to where y, for example, y here equal a function of x. All right. So that's the f. That's the f reverse. Okay, f reverse. So you could f reverse. Okay, it's a one-way. This is two-way function in here. This is a two-way function. All right. So one-way function. However, this is one-way function, but we can go back because we have something called a trapdoor. A trapdoor. Okay, we'll talk about trapdoor in a second. Okay. So one-way function, or we call it OWF, one-way function. F is easy to compute. What is F? This is F. Okay. F reverse, F inverse, okay, is difficult to compute. All right. So what we do, if we have one-way function with a trapdoor, then what we'll have, given y and a trapdoor, x can be computed easily. So this will be computed easily. So what we are using in here, one more. We're using a one-way function with a trapdoor. Okay, with a trapdoor. All right. So example. Okay. So when n is a large, n, a number is large, n equals p times q, and p and q from math lecture, p and q, they are prime numbers. They have to be prime numbers. So if we can divide any number, big number, in two numbers, multiply them together, and these two numbers are primes, okay, is a one-way function. So given p, if you have a p, okay, and a q, it is always easy to calculate n, right? If you have p and q, can you calculate n? Yes. All right. Given n, it is very difficult to compute p and q. If the n is so big, it's like 300 digits. Is it easy to calculate p and q, to know what's p and q? It's very hard. Possible if you have a very complex supercomputer, okay, but it's very hard. So this is what we call it one-way function. All right. Remember that when you decrypt, you need to decrypt it in real time. You don't want to wait 100 years to get the decryption, right? Right? So it's okay. So it is always easy to calculate n. Given n, it is very difficult to compute p and q. This is a factorization problem. And again, we explained factorization in the previous chapter.
So, this has nothing to do with the Diffie-Hellman problem?
It could. We're going to talk about it in the next chapter. Okay? All right. So when n is large, the function y equals, if you need to calculate y, it will equal, this is another example. The function y equals x to the power k mod n is a trapdoor one-way function. So this is one-way function. This is a trapdoor one-way function. Why? If you are given x and k, and n, it's easy to calculate y, right? Right? It's very easy, right? It's this. So if you have x and k and n, it's very easy to calculate y. Given y now, and k and n, it is very difficult to calculate x. Very difficult to calculate x. So if you know the y, you know k, you know n, you cannot calculate x. It's very difficult. Why? Because this is the discrete logarithm problem, which is very intensive computing, right? However, if we know the trapdoor, that's the key. If we know the trapdoor, what is the trapdoor? K prime, okay, such as k times k prime equals 1 mod phi n. Phi n we explained in the last lecture, okay? Okay, we can use x, if we know the trapdoor, we could use x equal to y to the power k prime mod n to find x. So the trapdoor here is k prime. If you don't know k prime, it's a one-way function. If you know k prime, it becomes a trapdoor one-way function. The trapdoor is the way it will make the computation is easy for it. All right. So what's the definition for k prime? Here, k times k prime will gives you 1 phi n. Phi n. Okay. What is phi n? N, it will be divided in 2 primes. Okay. So if we have 2 n, for example, okay, 2 times 2 is 2 have 2 primes, 2 and 3 and 7, right? These are primes. So n equals, right, which is 21. Phi n, so this we call it q, and this we call it p. So phi n equals what? Equals q minus 1 times p minus 1. Q minus 1, how much? 2. Times 7 minus 1, 6, right? Equals 12. That's phi n. If we go to the previous chapter, we explained that, okay? Alright? Alright. Alright, so Alright, so what's the difference between example 10.1 and 10.2? This is one-way function. How about this?
Trapdoor.
Is a trapdoor one function. All right. So let's take, let's explain it with one of the protocols, Knapsack crypto system. Knapsack crypto system. So the definition says that, okay, we have A, which is built of a matrix, one row, A1, A2, AK, and X is X1, X2, and up to Xk. So what is the size of the A? It's like K digits, for example, and then here is K. So to calculate the knapsack, okay, for A and X, we multiply and add. So A1 times X1 plus A2 times X2 times A2 until the end. The X's are digits 0 and 1. So either 0 or 1, right? And then here could be any digits. So for example, if I So I could use, for example, A equals 3, okay, 6, 7, 2. And X equals 0, 1, 1, 0. So the knapsack will be how much? 3 times 0 plus 6 times 1 plus 7 times 1 plus 2 times 0. Let's make the times like that to make it more clear. So that equals 0 plus 6 plus 7 plus 0. And make it equals to 15. Alright? Okay. So given A and X, it is easy to calculate S. We calculated it very easy. That's the rule. That's a function. Easy, right? However, given S and A, it is very difficult to. So if I have 13 and I have the A, is it easy to calculate X?
No.
It's very difficult to calculate X. Alright? It is difficult. Okay. So to make a trapdoor, as a trapdoor, we make it increasing. So we make it increasing. So AI is bigger than all the previous ones. So for example, this does not apply. Let's try one more. So for example, okay, so, all right, so A equals, let's start with a 3. Okay, what could be the next one? 4. What could be the next one? No?
8.
Huh? 3 plus 7?
8.
3 plus 7, how much? 7. It has to be bigger than, so it has to be 8, or 7, or 9, or whatever. So now 8 plus 7, how much?
15.
15. So this could be 18, for example, or 20. Make it 20. Okay, the next one has to be bigger than 15 plus 20, which is 35. So you could say 40. This is good. So it's increasing, right?
So it should be more than the sum of the previous numbers.
Previous ones, and that's what we have in here. So
Okay.
AI is bigger all the previous ones. Okay? Why? Because we need to be able to calculate the x's. Let's take example. So that's the algorithm. Look in here. So as a very trivial example, assume that A equals 17, 25, 46, 95, 201, 400. Are they increasing? So let's try it. 17 plus 25, how much?
42.
How much?
42. 42.
25, 32. The next one, 47. It's bigger, right? If you add these together, the 94 will be more, and so on and so forth. So it apply the condition. And S equals to 72. So we know now A, and we know S. We need to calculate X. What is X? Zeros or ones, right? So argument, the table 10.1 shows how the tuple X is found using inverse knapsack sum routine in algorithm 10.1. In this case, X will equal this. So what we do, so we start from the, we know what is the size of X, how many elements? 6. Why? Because we have 6 in here. So we start from 6, right? So you put the AI. How much AI? The last one? 400. How much S? 272. Okay, we'll check if S bigger than the AI. So is S 272 bigger than 400?
No.
False. Then definitely the X, how much?
0.
6 equals 0. Right? Right? You understand this, okay? Then now we switch. So now we keep in S272. We move 272 in here and we go with the next one. How much? 201. So is this bigger than this?
Yeah.
True. Then definitely X5 is 1. Then the difference is how much? Remaining 71. We move 71 here and we move the third one, 94. So is 71 bigger than 94? No, false. Then X4 how much? 0. And then we remain 71. We did not subtract that, right? We move it here and 46. We keep continuing, right? And this is in here. So we were able to have this trapdoor when we made a condition that it will be increasing. If I don't have that condition, I will not be able to do that. Okay? And you see, we were able. So this is one-way function with a trapdoor. Alright? So this is an example, for example, secret communication with knapsack. Okay? So again, any algorithm is like that. So the first thing we start with where? With the key generation. With the key generation. So in here we have to select B, which is B1, B2, Bk. Select B. Okay? Then select modulus N and R. Okay? Modulus N and R. Okay, then calculate A. Alright? Then the private key is 3 elements, which is B, R, and N. The public key will be is A. So A, you share it with every one. A, you share it with every one, and these you keep them as a private. And there is an algorithm. So this is an algorithm to generate the key. And there is algorithm here for encryption. So encryption, what you do, knapsack sum X, okay, with A. What's A? Is the public key. What's X? Is the data. You're gonna send it, and there is a procedure in here how to reverse it. So for example, you start with S prime equals R minus 1. Where is R? It was selected as a private. Times S. What is S? Is the message delivered, right? Then X prime inverse, and then X permute for X. Okay. So algorithm for generation, algorithm for encryption, algorithm for decryption, public key, private key. Public key, private key. Alright? So what made it possible is the trapdoor we have created. So this is an example. This is a trivial, very trivial example. So in here, let's take about the key generation. So key generation. So for key generation, okay, Bob creates the super increasing tuple B. So 7, 11, 19, 39, 79, 157, 313. So that's super increasing. That's step number 1. Then Bob chooses the modulus N900 and R37. Okay? Choose two prime numbers, two numbers, right? Then then create and 2, 4, 5, 3, 7, 1 is the permutation table. All right? Choose a permutation. So he first of all gonna choose a B, then choose N, then choose R, then choose a permutation table. You know it's permutation table to switch. the location in the arrow, right? So Bob now calculates the tuple R. Okay, tuple R. Okay, right? So tuple R. Let me check what's. So the tuple R is calculated according to cubic, where is it? T, I'm sure, tuple T, okay, and there is a rule for that part of the algorithm. Tuple T equals to Ti equals R times B. So all you have to do, where is R? How much is R? 37 times 7 will give you this number. 37 times 11 will give you this, and so on and so forth. Alright? This algorithm, right? Then Bob calculates the tuple A, which is permutation of T. So this is T. So the first one, so this is the T. You have to permutate it. So the first one we start with number 4. Where is number 4? 1, 2, 3, 4. 4 becomes first. The second one is number 2. Where is number 2? 407 becomes 407. Then 3, then 5, I'm sorry. 1, 2, 3, 4, 5. 5 is 409, for example. What is 5? After 4, 2, 5. 1, 2, 3, 4, 5. 223, and so on and so forth. You permutate, you rearrange them, right? And then Bob publicly announces A. This is A. What is A in here? What is A? Is the public key. The public key. What is the private key? B and R and N. Alright? Then after that, what you're gonna do? This is for key generation. Now, suppose Alice wants to send a single character G. We said in asymmetric what we are transmitting? Digits. So I have to convert G to a digit. So G, okay, so she uses 7-bit ASCII representation of G, which is this one. Okay, in a binary. And create the tuple X. So what is the data we're gonna send? 11001111. This is the X. Okay? Then after that, what we have to do, we have to calculate the knapsack. Knapsack, how it will be created? So you multiply the X with the A. Okay? It gives you 2165. So that's the data encrypted. So what's the date? What's the plain text? G, which represented in a binary like this. What is the data will be transmitted? 2165. This is encrypted. Encrypted, right? So now at the receiver, Bob can decrypt the cipher 2165. So what you do, Bob calculates S prime, which is S times R inverse mod N. It will give you 527. Bob calculates the X prime, which is the inverse knapsack sum, will give you this, this matrix, right? Now Bob calculates X permutation, so we have to arrange it with the same permutation. So number 1 will go, where is it? Number 4. So number 4, where is number 4? It's 1, came in here. Then number 2, where is number 2? 1 will go in here, and so on and so forth, right? And by the end, it will give you this binary, it will give you the G. Okay? It will give you the G. Clear? Alright, so what we have learned so far? We have to use one-way function. Our plain text has to be digits. Alright? We have 3 algorithms. Algorithm for key generation. It's gonna generate how many keys? 2. 1 public and 1 private. We're gonna use encryption algorithm using the public key of the receiver, and we're gonna do decryption using the private key of the receiver. Okay? As simple as that. condition for the condition in here that we have to have a back door, trap door that you could easily calculate. We'll talk about RSA. I'm not sure why this stopped working. So we'll talk about RSA. It's the most common public key algorithm. Is the RSA cryptography system named for the inventors, three inventors. Okay. All right. So. Right. So basically, what you have to when you look at the complexity of the operation, okay. So to create the cipher, there is two keys. Okay, the first key is the public key, which is E, and the private key, which is D. All right. So to create the cipher, okay, C equals P to the power E mod n. This is polynomial complexity, which is easy to calculate. And to calculate the plain text, it's C to the power D, which is, what is D? Is the private key. So in here we have two keys, one public and one private. So what is the public key is E. What's the private key is D. Okay, actually, what's the public key? Two things, N and E. What's the private key is the D. All right. So we have to calculate E and D that they could work together. So if you use E as a power for the plain text, and if you use the ciphertext with a power D, it will give you the result. Okay, that's the tactic, right? All right. So RSA uses modular exponentiation for encryption decryption. To attack it, E needs to calculate P. Okay, if you calculate C using this way to calculate P, you have to calculate C to the power E, and this is very hard to compute. It takes you forever to compute. All right. So encryption and decryption, that's what will happen. Let's take a look at the key. Let's take a look at the key generation. So with the key generation, what you have to do, you have to pick public and you have to pick two numbers, P and a Q. P and a Q have to be primes, okay, and not equal. Then you calculate N. How you calculate N? P times Q. Then you select E and D. We'll show you how to select an E and D to reverse each other. E and N will become the public key. You share it with everyone. D will become the private key. So very simple. What's the public key? E and N. What's the private key? Is D. If you have a data, all you have to do, power it to E mod N and send it. The data you receive, power it to D, it will be C power D mod N, will give you the data. So that's the algorithm. So we know the algorithm for key generation, and we know the algorithm for encryption, and we know the algorithm for decryption. The only thing we need to know now how to calculate E and D to work together. Right? We need to figure that out. So, two algebraic structures for encryption decryption is R in Zn plus multiplication, and key generation group is in Z phi n. So RSA used two algebraic structures, R and G. R is A tuple E, N is the public key, and D is the private key. So very simple. What is the algorithm in here? Very simple. So for key generation, we choose P and Q. They don't equal to each other. They are primes. We calculate N. Then after that, we calculate phi N. What is phi N from previous lecture? It's P minus 1 times Q minus 1. That's phi N. We save it in phi n. Then we select E such as E is bigger than 1, larger than 1, and smaller than phi n, and E is a co-prime with the phi n. A co-prime with the phi n. Alright? So now you select E, any number, okay, any number in the range. It has to be from 1 to phi n. Right? So in our example, where is phi? Did we calculate phi n in here? Whatever. So it was 12, right? The phi n. So phi n, if it's 12, the number you're going to choose is between 2 and 11. 2 and 11, right? Then you calculate the reverse, the multiplicative reverse of E minus 1, it will be D. The multiplicative reverse of it will be D. Alright? So public key will be E and N, and the private key will be D, and that's what we're gonna share. That's what you will share. Alright? So this is the algorithm for encryption. So encryption, okay, and this is for decryption. Let's take example. The best thing right away go for example. Okay. Okay, this is an example. Okay, that's an example. So Bob chooses 7 and 11. Is 7 a prime?
Yeah.
11 prime. This P and a Q. As P and a Q, and calculates N. What is N? P times Q. How much? 77. Clear? The value of phi n. What is phi n? 7 minus 1 times 11 minus 1. How much? 60. So now he chooses two exponents, E and D. Now that's a trick. Steps that you have to choose E and D. E has to be in range from where to where? 2 to 59. Okay? Okay? Okay, but it has to be in Z60. That means, what does it mean it has to be in Z60 asterisk? That means it has to have multiplicative inverse. Right? So one of in that range, but it has to have multiplicative inverse. Right? We already studied that, right? So if he chooses E to be 13, okay, 13, okay, then D is 37, because the multiplicative inverse of 13 in Z60 asterisk is 37. And you know how to calculate the multiplicative inverse, right? So if you multiply 13 times 37 mod 60 will give you how much? 1. Alright? So note that E times D mod 60 will give you 1. They are inverses of each. Now imagine that Alice wants to send a plain text 5 to Bob. A plain text 5. Okay, 5. Alright, to Bob. She uses the public exponent 13. Why 13? What is 13? Is E. What's E? Is a public key. Alright, so how you do that? Plain text is 5. C 5, which is the plain text, to the power 13 mod. Okay. Mod how much? Mod how much? N. How much N? 77. Will give you 26. So what is this 26? It's a ciphertext. It's a ciphertext, right? Alright. Now, for decryption, what you have to do, 26, which is a ciphertext, to the power of 37. What is 37? D, which is the private key, will give you what? 5. That's encryption, decryption. So encryption, decryption, very easy algorithms. Where is the trick? In calculating the private and they have to work together. Okay? According to the algorithm. According to the algorithm. So in here, let's take another example. Okay, now assume that another person, John, wants to send a message to Bob. John can use the same public key announced by Bob. Public key. Okay, 13. John's plain text is 63, right? So you have in here 63 to power 15 gave you how much? 28. Now Bob receives the 28, which is in here, and it's gonna use the same private key. Okay, gave you 63. So this pair gonna work in any plain text and ciphertext. It will work, right? All right. All right. So let's take trivial examples. Jennifer creates a pair of keys for herself. She chooses P, this number, Q, this number. Both are primes. Both are primes. She calculates N, multiplying this by this, give you that big number. She then calculates phi N, give you that number. She then chooses 3, 4, 3, and D, this number. So E and D. Show how Ted can send a message to Jennifer if he knows E and N. If he knows E and N. What's E? The public key. And N is other part of the public key. Okay, so suppose Ted wants to send a message no to Jennifer that changes each character to a number. So from 0025, with each character coded as 2 digits, he then calculates the 2 coded characters and get 4-digit numbers. The plain text will be 1314. Okay, 1314 is, will be the number. Okay, so what we have in here, we have the plain text, we have the E, we have the D, we have the N, right? Alright, so very simple in here. Ted, there is no. The plain text is 1314. So 1314 to the power of E. Mod N gives you C. And here you'll have C to the power of D. Mod N give you the same data. Yes?
Are we going to carry out this kind of calculations in the exam?
Huh?
Are we going to carry out this kind of calculations in the exam?
No, much bigger than this. I'll show you in a second.
Are we going to use calculator or?
No, you have to learn how to do multiplication. This is, did you read what we said before in here? Trivial example. I'll show you what you're going to do in the exam in a second. Okay, this is a trivial example. I'll show you in a second what you're going to do in the exam. Okay? Alright, so you understand the algorithm, how it works?
Yeah.
Okay? Now, this section talks about the problems, and I'm going to skip it for a second because I'm going to show my friend how is real data. That's what you're going to do in the exam. In the real life, that's the plain text. You see how much? You see P? Alright? And that's a Q. Okay? Q. And that's N. You multiply Q with N. And the phi N, that's a phi N. That's real life, right? Phi N. And that's E. And that's D. And you have to do it in the exam without a calculator. Right? Alright? So let's take example. That's the plain text, and that's the ciphertext we're going to create with that P and Q and N. That's the ciphertext. From that to here, okay? And that's the plain text. Okay? Happy? Happy? Okay? So we'll continue on next lecture. Okay? Continue next lecture. But that's RSA. RSA, one of the most algorithm used for asymmetric encryption. Okay? And we're gonna talk about 3 more asymmetric encryption techniques. Little bit, different than RSA, but there is many of them. In this class, we'll talk about maybe 4 total. Okay, but you got the idea. The idea is you have to have an algorithm to generate the keys. The keys are 2, public and private. All right, then encryption and then decryption. Understand? Yes, sir.
Yeah.
So I learned that RSA is one of the first arithmetic
Asymmetric?
asymmetric encryption mode. Is it still in use in this modern age?
Absolutely. Remember the first slide what we said? Symmetric and asymmetric, they complement each other. They use for different applications. I mean, you cannot use one without the other. So for digital signature, that's what we use. We did use symmetric. We'll come to it. So definitely, I mean, that's used every day. They complement each other. There's different applications for it. Digital signature, for example. How you can create digital signature? Do you know what's digital signature? Huh? Yeah, so using RSA. Okay? Hard disk encryption, what are you gonna use?
Symmetric.
Symmetric. Not ES or this or triple this or whatever it is. Okay, different applications. Okay, I'll see you Thursday. Thank you.